This is sections 4.1 to 4.3, solving systems of linear equations. I always like to start off this section with a nice visual example. So what is a system of linear equations? A system of linear equations is two or more linear equations that we want to set or solve all at once, or satisfy at once, I should say. So we're trying to find a point or a set of points that will give us a solution to more than one equation, okay? An example of a solution of a 2x2 system of equations. So a system of equations. We usually use brackets to hold all of our lines. So we'll have two lines, something like ax plus by equals c, and I don't know, what's after c? Dx plus ey equals f. So we have two linear equations, okay? This is an example of a system, a 2x2 system. And what is our goal in this section? We want to find an ordered pair x comma y, or a point x comma y, that satisfies both equations. That is not how it's supposed to satisfy. All right, so we're trying to figure out, we have two lines. We want to find a point that's a solution to both of the linear equations that we're given, okay? Before we jump into how to do this algebraically, I want us to just think about, well, what are the possibilities for how our two lines can interact with each other? And I think the best way to do that is to draw it, sorry, let me erase this. What is this? I don't like straight lines. All right, so the best way to illustrate this is to draw out our three possibilities for how two lines can interact with each other. So case one, we can have two lines that cross at some point, okay? Two lines that intersect. So maybe this is our f of x, and oops, let's use a different color. This is our g of x. All right, so we have these two lines. Our first case is we have two lines that cross. All right, if the two lines cross, then there's only going to be one point that gives us a solution to both of these equations. That point would be the intersection point. So this intersection point here would be the solution. Okay. I'm going to come back to some special names that we have for these things. We have one solution versus having multiple solutions. Okay. All right, so that's case one. Our two lines intersect. Case two. It's possible that we have two lines that are parallel to each other. So if the two lines that you're given end up having the same slope but different y-intercepts, they're going to be parallel to each other. And how do parallel lines intersect? They don't. If we have two parallel lines that never intersect, there are no points that are going to satisfy both of these equations. So that means they share no common points. There would be no solution in this case. Okay, and then our third case, it's kind of hard to draw, but we'll do it. Sometimes you're given two lines that are written differently, but they actually end up having the same graph. Okay, meaning the lines might be written in different forms, but they simplify to the same slope-intercept form. So they end up giving you the exact same graph. An example of that would be something like x plus y equals 2, and 2x plus 2y equals 4. these linear equations look different, but when we write them in slope-intercept form, we get the same slope-intercept form and they have the same graph. So if we had this system where we graph these two lines, turns out the lines are going to be, well, that's actually a decreasing line, but that's okay. The lines will end up being right on top of each other. I'm going to try to draw them right next to each other. So in this case, the two lines are actually the same graph, which means that they share all of their points. So any point on the line would give us a solution to the system of equations. It would work, right? This is an example where you have infinitely many solutions. Every single point on the line is a solution, okay? So infinite solutions, and we find the solution by finding a point on a line, or either line, every point on the lines. All right, so these are the three possibilities when we look at a 2x2 system of equations. We either have that the two lines are intersecting, and we have one solution, and that solution is the intersection point, or we'll have that the two lines are parallel to each other. Parallel lines have no solutions. Or finally, we'll have that the two lines actually have the same graph, they're the same line. So the lines are on top of each other. I should draw arrows on these. It's going to bother me if they don't have arrows. The two lines are on top of each other, and every single point on the line would be a solution. All right, so graphically speaking, when we have to solve a system of equations graphically, we graph our both lines and we want to look at which of these cases we have, and we can figure out what our solution is. But we also want to focus on being able to solve systems like this algebraically. So if I just give you the two equations without graphing, I want you to be able to determine if there's one solution, no solution, or infinite many solutions. Okay, and we do that using two different techniques. One is called the substitution method, and one is called the elimination or addition method. Okay, so we'll start off with an example using the substitution method. Solving a system algebraically using substitution. All right, so the first system we're going to try to solve algebraically using a method called substitution will be x plus y equals 1 and 6x minus 2y equals -10. Usually when we're given a system of equations, our lines are given to us in standard form. Sometimes they're given to us in slope-intercept form. But usually we like to line up the system to have our x's plus our y's equal our constant. So write them in standard form. From here, the idea behind the substitution method is we want to find an x and y that works for both of these equations. If I can take one of the equations, solve for one of the variables, and then substitute it into the second equation, I'll be able to solve the second equation for the remaining variable, okay? So there are steps for doing this. Our first step is going to be I'll write it out here. Step 1, you want to look at your system. Usually there's going to be one equation, sometimes both of them, where it's easy to solve for one of your variables. So if we look at these two equations, x plus y equals 1 and 6x minus 2y equals -10, the second equation has, more numbers in it, so it looks a little bit more complicated. But in the first equation, it will be really, really easy for us to solve for either x or y, because the x and y there have a coefficient of 1. So look for one of your equations where either x or y has a coefficient of 1, and then solve for that variable. For the first one, like I said, since both x and y have a coefficient of 1, we can solve for either one. Okay, so step 1 is use one of the equations to solve for one of the variables. It usually doesn't matter which one. You want to pick whichever one is easiest. And like I said, in this case, it would be easy to solve either, or to use that first equation to solve either one of these. So for our solution here, using x plus y equals 1, we can solve for x, okay? That'll give us x is equal to 1 minus y. That's our first step here. So take that first equation, solve it for x. You could have solved it for y too, but we're going to do it by solving for x. All right, second step. The idea is we want to take what we just found, what we just solved for x, and substitute that into the second equation. So for step 2, take the equation from step 1, or the expression from step 1, and substitute it into the other equation. So take the expression from step 1 and substitute into the other equation. And when I say other equation, for step 1, you use one of the equations. When you substitute, you don't want to substitute back into that equation that you used for step 1. You want to substitute into another equation, or the other equation. All right, so what we're going to do here for step 2, we're going to use x equals 1 minus y and substitute into 6x minus 2y equals negative 10. All right, let's do that. That means we're going to replace the x here with 1 minus y. So where the x was, we're substituting in a 1 minus y. So we get 6 times 1 minus y minus 2y equals negative 10. All right, what's the point of this? All right, in order to solve an equation, we only right now have techniques for solving equations with one variable. So if we have something like 6x minus 2y equals negative 10, we can't solve for x and get a number, or solve for y and get a number, because we have two variables. But now when we make this substitution, if we replace the x with 1 minus y, we end up with an equation that only has one variable. Our equation now only has y's. This will allow us to solve for y. Okay, so that's step 3. Solve the equation that you get in step 2 for the remaining variable. All right, we solve this. We get 6. We have to distribute. I'll just rewrite the whole thing. So we have 6 minus 6y minus 2y equals negative 10. That will give us 6 minus 8y equals negative 10. We can subtract 6 from both sides. If we do that, we get negative 8y equals negative 16. Okay, and then from here, y would be equal to negative 16 divided by negative 8, which is 2. Yay! We found our y. Are we done? We've solved for something. Boom. Does that mean we have our final answer? No. Very, very important here. When we're solving systems of equations, our answer is going to be an ordered pair. So we found the y, we still need to find the x. Okay? How can we find the x? I want to move all of my steps. They're in the way. But how can we find the x? Now that we know what y is equal to, step 4 is going to tell us to take this solution and plug it back into our other equations. So we go back here, plug it back into one of these equations. Technically, you can use either one, but it's easier to use the first one. So substitute the answer that you get into one of your equations to solve for the other variable. So we'll plug in y to solve for x. So step 4, substitute. Notice we're doing lots of substitutions. That's why this is called the substitution method. So substitute the solution from step 3 into one of the original equations to solve for the remaining variable. All right, so in our case, and we have to scroll up a little bit, our original equations were x plus y equals 1 and 6x minus 2y equals negative 10. I'm going to use x plus y equals 1. Yes. All right. So we have x plus y equals 1. We're going to substitute in 2 for y. So that gives us x plus 2 is equal to 1. And then if we subtract 2 from both sides, x is equal to negative 1. All right, so we have our x, we have our y. Final thing we need to do here is write our solution as an ordered pair. So last step, writing out our solution. Solution, you want to write an ordered pair, x comma y. So it would be negative 1 comma 2. And that's it. Yay, we've solved the system using substitution. Let's follow through our steps again really, really quickly. What did we do here? We started off by taking one of the equations and solving it for one of the variables. We took the first equation and solved for x. Then we substituted what we got into the other equation, and that gave us an equation that only contained y's. Great, now we can solve that. We solved for y, then we use what we got for y to solve for x, and boom, we have our ordered pair. All right, off to the side over here, I want to go through and check our solution. Okay, let's check our answer. We got that the solution was negative 1 comma 2. That means if we plug in negative 1 for x and 2 for y into either of these equations, we should get a true statement. Okay, so for equation 1, x plus y equals 1. That would be negative 1 plus 2 equals 1. Does negative 1 plus 2 equal 1? Yes, 1 equals 1. That checks out. So this ordered pair does work for the first line. And then for the second one, 6x minus 2y equals negative 10. That's 6 times negative 1 minus 2 times 2 equals negative 10. Negative 6 minus 4 equals negative 10. And yes, both sides are equal again. So this also checks out. If we plug in the ordered pair into our original equations, both equations should be satisfied. All right, we did our first example there of solving a system using substitution. Any questions about any of the steps that we did? Also, these steps listed all together can be found in your book in section 4.2. So on the second page of section 4.2. All right, that's our first example. Let's do a couple more. Also, this is an example where you have one solution. Actually, let me take it back. Before we go on to another example, I want to talk about how we could solve this graphically as well. To solve this system graphically, this is the easier way, but there is a little bit of work. We want to take the original equations, x plus y equals 1 and 6x minus 2y equals negative 10. In order to graph these, we have to have them in slope-intercept form. So we're going to write in slope-intercept form. That'll give us x plus y equals 1 becomes y equals negative x plus 1, or you can write 1 minus x. And then 6x 6x minus 2y equals negative 10 would be negative 2y equals negative 6x minus 10, dividing everything by 2, or negative 2, y is equal to 3x plus 5. So these are the slope-intercept forms of these equations. We're going to plug these in for our y1 and y2, and then find the intersection point. Let's do that on Desmos really quickly. So we have negative x plus 1 and 3x plus 5. Negative x plus 1, it's down there somewhere. 3x plus 5. All right, I got to zoom out here. When we zoom out, here we get a graph of both of the lines. And when we click on this intersection point, we get the solution that we found algebraically. This is an example where we have one solution. That means that these two lines cross or intersect at one point, and that intersection point gives us our solution to the system. Negative 1, 2. All right. Any questions about example 1 before we go on to our next example? I did call this example 1, right? Yes, that's example 1. So now we're on to example 2. This time we're going to have the system x minus 3y equals negative 5, and 3y equals 5 plus x. So these aren't both given to us in standard form, but that's okay. Let's see. In the first equation, the x has a coefficient of 1, and in the second one. So it'll be really, really easy to solve for x using the first equation, so we'll do that. I'll summarize my steps a little bit quicker this time. So for step 1, we have x minus 3y equals negative 5. So that gives us x is equal to 3y minus 5. Okay. For step 2, we're going to substitute 3y minus 5 into the second equation for x. So we have 3y equals 5 plus x. We're going to replace this x with the 3y minus 5. So this becomes 3y equals 5 plus, instead of x, we're replacing it with what we solved for in step 1. 3y minus 5. All right, and then step 3 is to just solve this equation. So step 3, we want to solve 3y equals 5 plus 3y minus 5. First, on the left-hand side, on the right-hand side, we have a 5 plus 3y minus 5, that simplifies. Then we just get 3y is equal to 3y. This is an identity. If you end up with something like this, 3y equals 3y, that's true for any value of y. But if you wanted to take it a step further, we can move all of the y's to one side. We subtract 3y from both sides, we get, so let's see, we do minus 3y and minus 3y, that gives us 0 equals 0. All right. This is an example of a solution that has, a system that has infinitely many solutions. If you try to solve your equation and you end up getting 0 equals 0 at the end, the x's cancel out, the y's cancel out, we're just left with 0 equals 0. That means that it doesn't matter what our x or y value is, these two equations are always equal. So this equation is always true. Okay, this means that we have infinite solutions. Okay, how do we have infinite solutions? These are actually just the same line. They're written just a little bit differently. So any point that's on the line would give us a solution to the system. The way that we write up our solution set in this case would be to say that there are infinite solutions. But then we can't just pick any point in the plane and say it's a solution. Our infinite solutions are all the points that are on the line. So we'll write it in set notation. The solutions are this, yeah, that's right. The set of all x comma y. So that's any point that's on the line that we're given there. 3y equals 5 plus x. I'm going to come off to the side here. We can write this in slope-intercept form. If we divide everything by 3, this is y is equal to 5 over 3 plus 1/3 x, or y equals 1/3 x plus 5 over 3. This is a line we're given in the system 2 times. So if we pick any point on this line, that's a solution. So y equals 1/3 x plus 5/3. Right. This is how we want to write out our answer. This is saying that there are many points, infinitely many points, that satisfy this system of equations. If we pick any point that's on the line, 1/3 x plus 5/3, it'll give us a solution. And the big key takeaway from this point is, well, how do I know that there are infinitely many solutions? When you try to solve algebraically and you end up with 0 equals 0, that means that there are infinitely many solutions. That means that the equation is true all the time for any value of y. All right, I'll pause here really quickly for questions. Any questions? All right, then let's do one more system. Well, we'll actually do 2 more systems. 2 more systems. We had an example where we had 1 solution. We had an example just now where we have infinitely many solutions. So we need to see at least 1 example where we have no solutions. So I've given you, well, I don't know, we might have no solution. Let's see. The next example actually isn't no solutions. I want you guys to try one really quickly. Try the system. This is a good one. 3x minus 12y equals 6. And 2x minus 6y equals 4. All right, I'll help you get started here, but I want you to take a couple minutes to try to do this one on your own. And we'll go through the solution in just a minute. To start this problem off, you want to pick one of these equations and try to solve for one of the variables. Either solve for x or solve for y, whichever you find easiest. Here, since neither of the variables have a coefficient of 1 in either of the equations, then it doesn't really matter which equation you pick or which variable you start with. They're both equally difficult. So for instance, we can say in the first equation, 3x minus 12y equals 6. We're going to solve for x. Then x would be 3x equals 12y plus 6. Dividing everything by 3, we get x equals 4y plus 2. And then I want you guys to try from here. Using x equals 4y plus 2, substitute that into the second equation, and then see if you can find your value for y and use that value of y to find your value of x. I'm going to give you a couple minutes to do this. All right, so Jeremy wants to share his answer. Tell me what you got.
For x, I got 2, and for y, I got 0.
Yes, 2, 0 would be the correct ordered pair. Let's go through the solution here. So x equals 4y plus 2. Then for our next step, we're going to take 2x minus 6y equals 4 and substitute for x. So we'll have 2 times 4y plus 2 minus 6y equals 4. This gives us 8y plus 4 minus 6y equals 4. And then 2y plus 4 is equal to 4. All right, from here, subtracting 4 from both sides, 2y equals 0. So y would be equal to 0. Sorry, this is steps 2 and 3. Step 2 was substituting, step 3 was solving. And then step 4, we can use this y equals 0 and substitute it into the first equation to solve for x. So let y equal 0. Then we have 3 times x minus 12 times 0 equals 6. 3x plus 0 equals 6. So 3x equals 6 and x equals 2. And remember, when you write out your solution, we want to write an ordered pair, 2, 0. Very good. Any questions about this? All right, I just want to do one real quick example of what it would look like algebraically if we have no solution. We said that we have no solution when we get two equations that have the same slope, but different y-intercepts. If they have two parallel lines, and that should make sense because they don't intersect. But how would that look algebraically? How would you know? All right, let me make up a system that would work like that. So if we have negative 6x plus 2y equals 8, and 6x minus 2y equals 10. That should work. All right. When we try to solve this system using substitution, let's use the first equation to solve for, it might be easier to solve for y. So negative 6x plus 2y equals 8. That gives us 2y is equal to 6x plus 8. And then y would be equal to 3x plus 4. All right, then we substitute this into the second equation. So for 6x minus 2y equals 10, we replace the y with 3x plus 4. So we get 6x minus 2 times 3x plus 4 equals 10. All right, then we solve this. That's 6x minus 6x, and then we would have minus 8. If we distribute that negative 2 equals 10. And then this is where the problem comes in. The x's cancel out, and we end up with negative 8 equals 10. Is it possible for negative 8 to equal 10? No, it's not possible. So if you end up with two numbers at the end that are equal to each other, that aren't actually equal to each other, then this can't happen ever. So that means that there is no solution. These are parallel lines. All right. Now, I do want to do, I know it's 9:25. We need to look at the lab, but I do want to do one or two examples where we use the other method for solving algebraically, which is called the elimination method. So first, let me write down the steps for the elimination. So solving a system using elimination. All right, step 1. The idea behind the elimination method is we're going to take our two lines. We want to line them up so that the x's are lined up together, the y's are lined up together, and the constants are lined up together. And then we want to add the two lines together. But we want to do it in such a way that one of the variables cancels out. We are allowed to multiply one of our equations by a constant if we need to, so that the coefficients, say let's say we wanted to eliminate the x's. We're going to multiply so that the coefficients are opposites. That way, when we add the two equations together, one of the variables will be eliminated, hence the name elimination. All right, so step 1 is write the equations in standard form. Step 2 is, once you have the equations in standard form, figure out which variable you want to eliminate. Sometimes you'll have to multiply one of your equations, sometimes you'll have to multiply both, but the goal is to get the coefficients to be opposites. So if one has a 2x, the other should have a negative 2x. If one has a 5y, the other should have a negative 5y, at least for one of the variables. So multiply one or both equations. So the coefficients of one variable are opposites. Okay, once you have one of the variables having opposite coefficients, add the equations together. When you do this, one of the variables, the one with the opposite coefficients, will be eliminated. Okay, and then for part 4, solve the remaining variable. Okay, so you solve for one variable that's left. Once you have that remaining variable, then you can use the remaining variable to plug back into one of the original equations and find the other variable that was eliminated. So solve for remaining variable. And then just 2 more steps. 2 more steps. Step 5 and step 6. Once you solve for one of the variables, so let's say you solve for y, just like before, we use the remaining variable, use the variable that we solved to find the other one. So substitute the answer from step 4 into an equation to find the other variable. All right, and then step 6 is just write your solution as an ordered pair. Okay, so we should be able to do at least 2 examples with elimination, and then I'll stop because we'll basically almost be out of time. Okay, so solving systems using the elimination method. I think we're on example 5 at this point. So using elimination, we're going to solve the system. Oh, that one's not too bad. This one's easy. 2x plus y equals -1, and -2x plus y equals 3. All right, this one's beautifully set up for us. When we look at this equation, the lines are already in standard form. That's great. Also, if you look at the x's have opposite coefficients. So a little note here. Note the coefficients for x are opposites. So that's great. We can go straight to adding these 2 lines together. So we jump to step 3. So we add the lines. All right, if we add these 2 lines together, we add the x's. 2x plus -2x is 0x. So we have 0x. And then y plus y is 2y plus 2y. And -1 plus 3 is 2. All right, so we end up with 2y equals 2, which gives us y equals 1. Yay! We have one part of our ordered pair, okay? Once we have y is equal to 1, we can use y equals 1 to solve for x. So use one of the other equations, 2x plus y equals -1. We're going to substitute y equals 1. So 2x plus 1 is equal to -1. And then we're able to now solve for y. I'm sorry, solve for x. 2x would be equal to -2, and x equals -1. So our solution, if we put these two things together, is the ordered pair, -1, 1. Ta-da, that's it. We did it. So again, this one was nicely set up for us because the coefficients were already opposites. That's not always going to be the case. So I want us to do a problem where the coefficients aren't opposites or our equations aren't given to us in standard form, which means there'll be a little bit more work in the beginning. Any questions about example 5 before we go on to the last example? All right, example 6. Well, let's look at the system. 2x plus y plus 1 equals 0, and 4y equals -3x minus 1. First, you should notice right off the top that this system does not have both equations in standard form. So we need to put these in standard form. Okay. In the standard form, for the first one, if we move the constant to the other side, we have 2x plus y equals -1. That one's not too bad. And for the second equation, we need to add the 3x to both sides. So we'll have 3x plus 4y is equal to -1. All right, this is our system. So now, that's step 1. We've written them in standard form. For step 2, we need to determine which of these variables, x or y, we're going to try to eliminate. And then once we figure out which one we want to try to eliminate, we have to figure out how we can multiply the equations by a constant, as be a non-zero constant, so that the variable has opposite coefficients. Now here, x has coefficients 2 and 3, and then y has coefficients 1 and 4. Since one of the, did I write this right? Yes. Since one of the y's has a coefficient of 1, it'll be really easy to multiply to make that term whatever we want it to be. What do we want it to be? All right, so I'm going to say we're going to eliminate the y's. The second equation has a coefficient of 4, so we need to try to make the coefficient of the first equation, the coefficient of y in the first equation, the opposite of 4, or -4. So to do that, I'm going to write it out in words here. To eliminate y, we need the coefficients to be opposites. Okay, right now we have a 1 and a 4. To force them to be opposites, we can multiply the first equation by -4. Okay, so if we multiply that entire first equation by -4, we have 2x plus y equals -1. The second equation, 2x plus 4y equals -1. That's not going to change. We're going to multiply this entire first equation by -4 on both sides. All right. Then that gives us the new system, -8x minus 4y equals -4. And then second equation is the same, 3x plus 4y equals -1. Once you get here, where your one of your variables has opposite coefficients, then we're ready to add. All right, so now life's great. The y's have opposite coefficients. Let's add these together. Negative 8x plus 3x would leave us with negative 5x. Negative 4y plus 4y gives us 0y, and then negative 4 plus negative 1 is negative 5. So we end up with negative 5x equals negative 5. All right, then we can solve this. Negative 5x equals negative 5, and x equals 1. Yay, we have 1/2 of our solution here. Right, something feels wrong. Did I do something wrong? I don't know, I tend to believe me. Let me double check. Am I mathing properly? I made a little mistake. That's like 4 mistakes today. Bad, Miss Ross. I feel like I owe y'all a bonus point or something. No more mistakes for the rest of the semester. All right, don't hold me to that. I might make one little mistake, but minimal mistakes for the rest of the semester. All right, where did I make my mistake? I made a sign error. Here, we had -1 times -4, so that should be a +4. And then that changes our equation. We would end up with negative 5x plus 0y equals 3. And then negative 5x equals 3. And then x would be equal to negative 3/5. All right, but still, yay. Now we have that x. We're going to use that x. So use x equals negative 3/5. And you can use either of the equations. Is either one easier or is harder? It's not going to be easy or hard. Neither one is easier to use. So you can use either one of the equations, and then you want to solve for y. So we'll use the equation 2x plus y equals -1 to solve for y. All right. So if we replace the x with a negative 3/5, we get 2 times -3/5 plus y equals -1. That's -6/5 plus y equals -1. And then if we add if we add 6/5 to both sides, we get -1 plus -6/5, or plus 6/5 equals 1. Gotta make sure I still believe myself. I still believe me. All right, then we have to find a common denominator here. We can write the 1 as a -5/5. So this is -5/5 plus 6/5, which finally would give us a positive 1/5 for y. So finally, putting these two parts together, our solution to this system would be the fraction -3/5, comma 1/5. All right. So these are our two different methods that we use for solving systems of equations algebraically. You can use either the substitution method or the elimination method. Most cases, I don't ask you to use, I don't say specifically to use either one. Sometimes I do, but most of the time you'll be able to choose which one you want to use. Sometimes elimination is easier, sometimes substitution is easier. It just depends on how the system is set up. But with any system, you are able to use either one of them to solve. There are 3 problems on here, it's not too bad. The first one just says to solve the system of equations algebraically and graphically. For algebraically, you can use either of the methods, substitution or elimination. And for graphically, you want to graph both lines and show where the intersection point is. Your answers should match. Okay, so it says, do the answers agree? They better, because there's only one right answer. And then for problem 2, you're just given 2 systems where, again, you can solve using either algebraic method. And then problem 3 is the one that I want to talk to you guys about a little bit. So for problem 3, we're given a word problem, but from the word problem, we can set up two equations, and then we can solve a system of equations to find the solution here. It says a student takes, let me highlight some things here. A student takes 18 credits between day classes and night classes. The day classes cost $350 per credit, while the night classes cost $300 per credit, okay? The total of the student's tuition is $6,000. How many of each type of credit did the student take? Write the system of linear equations. Actually, I'm gonna change how I write this. All right, 2 bits of information that we're given. We're given the total number of credits that the student takes. And we're also given the cost of the day classes versus the night classes. And then when you have a word problem like this, we always want to go to the question. What is the question? How many of each type of credit did the student take? So we have to figure out what our unknowns are here. Here we have 2 unknowns. We're going to let X represent the day credits or day classes. And let Y represent the night credits. Or you can say night classes. But when it says we find how many of each type, we have 2 things that we don't know. So we have to figure out how many days and how many nights. Those are 2 unknowns, X and Y. All right, then we can write out 2 equations. Our first equation is going to be based on the number of credits. And then our second equation is going to be based on the cost. All right, we're told the total number of credits is equal to 18 credits. I highlighted that in red, so I'll write it in red. That means that when we take the number of day credits and add the number of night credits, that should be equal to 18, the total number of credits. All right. And then we can use the information given to us about the cost to find our second equation. We're told the day classes are $350 per credit. So if we take 350 and multiply by X, that's the number of day credits that we're taking. That tells us the cost for the day classes. And similarly, the night classes are $300. So if you do 300 times Y, the number of night classes, that gives us the cost for the night classes. And then we're also told that in total, we spend $6,000 on the classes. So this should be equal to 6,000. So from this information, we're able to identify our 2 unknowns, our X and Y, as the day credits and the night credits. We're able to write an equation for the sum of the credits. X plus Y should be equal to the total number of credits, 18, and write another equation for the cost. 350X plus 300Y should equal 6,000. This is your system. If you can solve this system for X and Y, that'll tell you the number of day credits and night credits.